Okay, so this is the topic on least square approximation. So, what is least square approximation? Wait, okay. So the problem statement is like this. So the problem statement is like this. If we are given uh, a vector b, let's say it has the size of m by 1, okay, we would like to find a multiplied with x, okay, where let me see, where a has the size of m by n and x has the size of n by 1, okay. So given a vector b, we want to find ax, okay, such that basically we want to use ax to approximate b such that the error from the approximation okay, or e, which is b minus ax, okay, is as small as possible. Okay, so this is a problem statement. We want to find ax to approximate b, okay, 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 such that the size of error vector square is minimized. So the left-hand side here and the right-hand side is the same. Okay. So that's what we want to do. So okay. So how do we do it? Okay, let's say that we look at a case of, let's say, like a 2D. Don't need to be 2D, but let me do it this way. Maybe I can explain from this approach. Okay, let's say that okay, let's say that A is consists of two column vectors. Okay. So we can take a look at this type of approximation like this. Okay. Maybe the vector b that we want to approximate, let's say this is b, let's say is equal to a vector, say 439, okay? And vector a's, let's say we have a1, we have a2, okay? Maybe a1 is equal to 110, maybe a2 is equal to another vectors, which is 250, okay? So in such a case, In such a case, A consists of two column vectors, which is A1 and A2. Okay. So the problem statement here is like this. So we have A times X equal approximate B. So I can write A1 and A2 like this. Okay. And multiply with X. So X is just the coefficient, X1 and X2, meaning that we want to combine A1 and A2 to approximate B. Okay. So that it approximates B. Okay. And this B is 439. So can we do it? So that's the question. So what we will do is we will use the concept that we saw earlier. Right? So this is what we will do. So we want to find X such that AX is AX approximate B. Okay, so that's what we want to find. And well, there are two ways to solve this problem. Okay, in this case, first of all, we do not consider the statistics of noise and so on yet. Okay, we just have vectors and then we try to approximate. Okay. If we consider noise or some random values, we will have a different approach to solve this question. Okay. So in order to solve for X, there are two approaches. Okay. Approach number one is to differentiate the errors, okay, and set it equal to 0 and then determines what X is. So that's one way. Okay. Another way, the other way is to use the concept from the projection that we looked earlier. Okay, that says that the error from the approximation is orthogonal. Okay, and that is called orthogonality principle. So we will use the approach number two. Well, you can do approach number one as well, but I want to use approach number two because it's simpler. Okay. So from the approach number two, which is orthogonality principle, which says that error from approximation or from projection, right? From approximation or estimation, okay, or from estimation or from projection, okay, is orthogonal to the vectors that you use. In this case, it's a vectors A. So we can say that E transpose multiplied with A will be equals to 0. Okay. And well, the dimension of E transpose here is anyway, so that's fine. I already did like this. So wait, what is the dimension of A? Dimension of A is M multiplied with M, right? Okay. And E is, what is E? E is B minus AX. B minus AX, right? So what is the size of A? What is the number of rows and column of A? Okay. B is what? B is M multiplied with 1, right? Okay. So AX, the size has to be M multiplied with 1 as well. So this E has the size of M multiplied with 1. Okay. So E transpose, this is 1 multiplied with M. So the dimension here is 1 multiplied with N. So this is a vector. Okay. And the error from approximation is just B minus AX. So we transpose, multiply with A, we get 0. Okay. Also, here we have E transpose multiply with A. We have dimension of 1 multiplied with N. So I should put a transpose here, because when we say a vector, we often say column vectors. Okay. So this will be like this. I can also, what I can also do is I can take a transpose on both sides. So then I have a transpose multiply with a minus ax, okay, equals to 0. Okay. So here from take the transpose of both sides. Okay. So this is what I have. And then I can just multiply the inside the parentheses, right? So I have, okay, I don't want to change the slide yet. So I have A transpose multiply with B minus A transpose multiply with A multiply with X equal to 0. Okay. And then I move one value to the one side. Okay. So I will have A transpose multiply with A multiply with X equals to A transpose multiply with B. Okay, just move one to the other side. Okay, because what we want to find is X. This is unknown. Okay, so I write X like this. I multiply A transpose times A inverse to both sides. So I have A transpose multiply with A inverse. Okay, and then I multiply with A transpose multiply with B. Okay, so this is when we do this, this is called the left inverse. Okay, so here we use the orthogonality principle for the approximation. So this is what we have for x. Okay, that's all. Well, it turns out that this is also can be called a minimum square error approximation, or yeah, or estimation. You can say that as well. Okay. So let's take a look at one example, what we are looking at. So I'm not going to work on the first approach, okay, because maybe one day we have to look at this derivative of matrices or vectors. We'll come back, okay. So let's take a look at an example from what we have seen, and then probably we finish. So example, okay. So let's say that you are given that matrix A is like this, 1, 1, 0, 2, 5, 4. This is from the previous slide, okay. And B is equals to 4, 3, 9, okay. So this is A, column vector A, A1, and this is column vector A2, okay. And we want to approximate B with AX, okay. So we want to find what is X, basically, okay. So we will use this result from this page, from this property, from this solution to approximate, okay. So we can just write X is equals to an inverse of A transpose multiplied with A, and multiply with A transpose multiply with B, okay. A transpose is just change from the row vectors to column vectors, right? So we have 1, 1, 0, 2, 5, 0, and multiply with vectors matrix A, which is 1, 1, 0, 2, 5, 0, okay? And then we take inverse. And then for A transpose multiply with B here, then we have 1, 1, 0, 2, 5, 0, multiply with B. B is 4, 3, 9. So what do we have here? So we multiply these. So this is 2 by 3. This is 3 by 2, right? So when you multiply, you get 2 by 2, right? So what do we have here? I do quickly. 1 plus 1 is 2. Okay, 2 plus 5 is 7. 2 plus 5 is 7, right? And then 2 plus 2 is 4. 4 plus 5 times 5 is 25. You get 29, right? And then you do inverse. Okay. And then you multiply here. Should I multiply directly? Okay, I can just do it. So here is 2 by 3. This is 3 by 1. When you multiply together, you get 2 by 1, right? So you get 2 by 1, no? So here you have 1, 1, 1, 0, multiply with 4, 3, 9, you get 4 plus 3, 7, right? And then here you have 2 times 4 plus 5 times 3, which is 8 plus 15, which is 23, right? Okay, so that's it. And we haven't talked much about it, but I can use the previous, the prior property that when you do an inverse of a matrix called A, B, C, D, okay, if you do an inverse, what you get is 1 over AD minus BC, and then you switch D and A, and then minus B minus C. So this is like a way of doing it, no? So AD multiply with minus BC, so we have 1 over AD, which is 58, and then 58, and then minus 7 by 7, multiply with 7, we get 49, right? And then this matrix, we have to switch A and D, we get 29 and 2, and put minus at B and C, we get minus 7 and minus 7, multiply with 7 and 23, right? So this is 1 over 58 minus 49, minus 49. Which is 9, right? And then, but what you will get is this number, which is 42 and minus 3, okay? So you can try that yourself, okay? So, so this is x, okay? This is x. And so this is what we find. This is x, which is x1 and x2, right? So we get x1 and x2, which is 42 over 9, and then minus 3 over 9, which is what? I divide by 3 on top and bottom. So I get 1, 4 over 3, and then minus 1/3. Right? Okay. So these are x1 and x2, which is used to multiply a1 and multiply a2. Okay. So this is x. So what is the approximation? Because we say that b is around ax, right? So I need to multiply this side. Okay, so this ax is approximation of b, because a is what? 1, 1, 1, 1, 1, 0, 2, 5, 0, okay. And for x I have, let me see from previous page, I have 14 and minus 1 and 1/3, 14 and minus 1, okay. So I just multiply. What do I get? I get 1/3. This is 3 times 2, and this is 2 times 1. So I'll get 3 times 1 as the result. So for the first one, I have 1 times 14 plus 2 times minus 1. So I have 12. Okay. And then for the second row, I have 1 times 14 minus 5. So I get 9. And the last row, 0 multiply whatever, it gets 0. So I get 0. Okay. So here I get 12 divided by 3. I get 4. And then 3 and then 0. Okay. So this is AX. Okay, which is used to approximate B. It's not equal to B, and you notice that B is 439. Okay, but because in this case A1 and A2, it doesn't have the last element or 0, so that's why when they approximate, you get 0 here. Okay. And then what else is the error? The error is just B minus AX, right? Okay. So you notice that the first two rows are the same, 0, 0, and then the last row is 9, okay, which is 9 minus 0. So this is what we have for the approximation. Okay, okay. So any question on this item? Okay. So this is the last topic for today. Okay. And I hope in the future we have time to look at the mean square error approximation for the system with noise characteristic. I'll try to cover as much as we can, but let's see what we can do here. Okay, so next lecture we will look at eigenvalue, eigenvectors, and also the singular value decomposition, or SVD, okay, which is one way of decomposition of matrices. In the early part of our class, we look at decomposition of matrices with LU factorization, LDW decomposition, right? And then maybe also we looked at Cholesky decomposition as well, okay? But next time we will look at an important decomposition, which is called singular value decomposition. And it's based on eigenvalue and eigenvectors, which has a lot of applications. Okay. And then for the two remaining lectures, we will look at random vectors and then apply that to common filtering. Okay, and that will be the conclusion of this course. Okay, so any question before we leave today? Some lecture, I will have a solution for midterm, and then we can look at the score. Okay. So G, please stop the recording at this point. Okay.